So in this video, I'd like to go over the Diels-Alder / Cycloaddition specific problems for the broader category of the pericyclic reactions. So I know I can talk a lot, so in the description I'll put the timestamps for the problems and then the following solutions if you just want to skip to those sections. First thing on the board right now, I just have two rules that are kind of helpful of determining if you have to consider endo versus exo product or determining where the regiochemistry of your molecule will end up putting different substituents. And so I would apply to these two rules, and I'll use them throughout the video. So let's get into the first problem. All right, so here I have just kind of standard diene that we usually work with when learning these types of problems, just butadiene, and then react it with this big molecule that has a bunch of nitrile groups in it. So go ahead and try to figure out what the product would be here. So product-wise, I'm going to recognize that I'm going to be adding 2 carbons. And for the sake of this problem, and I'll only do it for this problem just to save time, I'll show the mechanism. But the mechanism, if you're interested, it's going to be the same for all of these types of cycloaddition Diels-Alder type problems, where we just let one end of our dienophile attack one end of the diene, and we're going to have to move electrons around to satisfy carbon's 4 bonds, and we'll end up hitting the opposite side of the side that we started on for our dienophile. So this mechanism will be the same for the problems to follow. Again, we're recognizing we're adding the 2 pink carbons. That tells me I'm going to have a 6 carbon chain, so I can at least just draw that down. I can tell there's going to be a double bond right here that'll also be consistent throughout these problems. The middle of your diene. So if I call these 2 carbons in the middle, those 2 carbons are right here. That'll also be pretty consistent throughout these problems, having that double bond in between those 2 carbons. And if I wanted to say these pink carbons are the pink carbons that we added, that's just fine, because that tells us that these cyanide groups should be attached right here, just like this. No need to worry about stereochemistry because there is no chiral center at these 2 pink carbons. So let's move on to the second problem. So on this problem, I'm actually asking if we can, excuse me, I'm actually asking if we can do some retrosynthetic analysis. So we're starting with our product over here on the left. We can kind of see that double bond that we said was going to be characteristic throughout all of these problems. We are told that we have to find our diene because we know our dienophile is going to be ethane because that's given to us. So this is our dienophile right there. So the question mark, the orange question mark says, what is our dienophile? Or I'm sorry, what is our diene? So go ahead and try to figure that one out real quick. So figuring out what our diene is, we can go ahead and say that this carbon is pink, this carbon is pink. They will end up right here. And so I'm just going to have something that looks like a butadiene. So let's do something like this. That's also going to be characteristic that we're going to have 2 double bonds because as the terminology goes, diene means 2, and so di means 2, and ene means double bond. So there's your 2 double bonds, and now we recognize that we need the substituent that's hanging off, which is just a methoxy group. So this would be what our question mark was. So as retrosynthetic analysis, let's go on to another retrosynthetic analysis problem. Okay, in this problem, very similar, we said we were going to do retrosynthetic analysis. I'm telling us that we can use butadiene. Recognize it's not in its S-cis form, so if you wanted to, you could recognize and change it from the S-trans to S-cis. But basically, again, we're just trying to figure out what this blue question mark is. So give this one a try real quick. Recognizing that our diene is just the butadiene, our question mark has to be the dienophile. So remembering that what we've talked about, the diene is going to have that double bond in the middle of those 2 more centric carbons. And so we can kind of say that this carbon and this carbon correspond to that one and that one over there. So let's kind of draw what we know now. We know, well, actually, let me just do this. We can also designate this carbon and this carbon to be these last carbons. And so that kind of gives away the rest of what the question mark is really asking. So what is our dienophile? Well, it has to be all these other carbons and everything that's attached to. So it's easy enough. I'm just going to draw out everything that is there, and then we just have to designate a way that it's going to attack its diene. And we know we can easily do that by just adding a double bond. And so this would be what our question mark is representing. So let's go to the next. So back to the same type of problem that we did in the first one. We just want to figure out how these two things are going to go together. So go ahead and give this one a try real quick, and then we'll talk about it. So interesting thing about these, or just one part of this problem, is that our diene actually is in its S-trans form, and it has some substituents on it that we need to worry about. So the best way, I think, to go about these is not to get out a model kit or try to confuse yourself with your hands, but actually just recognize that if I actually color-coded one of these chlorines a different color, say that one's purple, let this, or we know that this purple chlorine is going to be cis. We can tell it's cis, the way it's oriented on the double bond, and the yellow chlorine is trans. So the whole entire molecule is in its S-trans form, and if we want to move it into its S-cis form, we can easily do that without even thinking, because we know it has to look something like that, something like this. And then we can place in the chlorine, the purple chlorine. We know it's supposed to be cis, so let's go ahead and let it stay cis. And the other chlorine we said was supposed to be trans. So now we've rotated our molecule into the S-cis form, and we know that this last chlorine is going to be trans. We can simply draw it in, and that would be what our molecule looks like in the S-cis form. So I think it's the fastest and easiest way that you can always get it right. It's foolproof. You can't mess it up with a model kit or with your hands. So it's a nice tool to use. But now reacting these two things together, what will we get? Well, recognizing that our dienophile actually is an alkyne, we can predict that we'll have two double bonds in our product. So we're adding two carbons. So there's the two double bonds. We add two carbons. So we have a 6-member ring. And the two nitro groups that are sticking out would be hanging out of these two carbons in the middle of that double bond. And the chlorines, we can say that the purple one, if we wanted to, it is on a wedge. And we can say that the yellow one is on a dash. Reasoning for that is because they are opposite in the reactant. So one is cis and one is trans. That means that when they react through the cycloaddition reaction, they will retain their opposite configuration. So one chlorine will be on a wedge and the other one will be on a dash. So this is your final answer. So this one, it's similar into the idea that of the last problem that we just did, except our substituents that we need to worry about aren't on our diene. This time they're on our dienophile. So that'd be these two nitrile groups. So recognizing we're going to only add two carbons, so we know it's going to be a 6-member ring in the end. So there's the 6-member ring right there. We know there will be a double bond right here and two methyl groups sticking out. And then the nitrile groups, where do those go? Well, because they're in the trans configuration, they're doing opposite things, so we should expect them to do opposite things in the product. So one of them I'm going to put on a wedge, and the other one, to be opposite, is going to go on a dash, just like that. And that's your answer. Okay, so let's go ahead and try this problem real quick, and we can talk about it afterwards. So in this problem, it's kind of nice because we're finally going to get to use one of those rules I had on the first slide of this video. I think it was the second rule I put out there, recognizing that the diene has symmetrical substituents. That should lead us down the road to thinking that we should expect some sort of an endo product. So now figuring out how the endo product will look sometimes can get confusing. So there's a clever way you can kind of think about it if you choose to do it this way. And it's going to be just putting your diene over your dieno file. So I'll kind of draw what that looks like. I'm going to draw it big so we can see. And there's an H right there. Just like that, if you drew it just like this, and then filled in where your H's are, I'm going to do them kind of color-coded. So this H is coming out right here, and maybe it'll do purple. This H is going out right there, and I can also put this H also purple going that way as well. So the takeaway here, the reason that we're doing this is that we want to know which way our hydrogens are actually pointing. So in our dieno file, the green hydrogen is pointing to the right. And in our diene, the purple hydrogens are also pointing to the right. So what that tells us is that when these two molecules come together, when they go through the cycloaddition process, the H's will still be doing the same things. So if I put them on if I put the green H on a dash, then the purple H's will also be on a dash. And you could also say I'm going to put the green H on a wedge, and then the same will be true for the purple H's. So let's kind of draw what this is going to look like. So when they come together, we're going to have that double bond still there, and I guess we can say these carbons are right here. So I understand it can get messy. Methyl groups, the methyl groups are still hanging out at those two carbons. And now the hydrogens. So I'm going to fill in the purple ones. Let's put them on a wedge. If that one's on a wedge, this one is on a wedge as well. Just like that. And now we know that the green H is doing the same thing that the purple H is doing. So let's put the green H on a wedge as well. Now, if that green H is on a wedge, then that means that the carbonyl part, so the aldehyde that's sticking out behind it, must be going back on a dash. So let's do this in red, and we'll show the dashing right here, and there's your carbonyl. And I can fill in that aldehyde H. So that'd actually be our product. And it's a nice little tool. It works best for acyclic type molecules when you start working with cyclic molecules and trying to determine endo versus exo. It gets a little bit messy doing this technique, figuring out what it looks like, but it will still work. You just have to be very clear about what your hydrogens are doing, what your substituents are doing, but it will still work. And so, of course, this product is our endo product. And we know the endo product is much more favored than the exo product. And this is a reason why. You could also talk about molecular orbital theory if you wanted to a little bit. That's why we have the carbonyl group hanging out behind, so to the left and behind our diene. We never are going to draw our substituent of our dienophile not lining up with the other carbon groups of our diene. So that's another good point I guess I can make. I could have instead drawn the dienophile like that, but then the orbital interactions of our aldehyde actually wouldn't be as ideal because they're not matching up as well with the diene as if I drew it on the other side, like it did the first time in red. So there's two little things you can keep into consideration: molecular orbital theory and this tool of figuring out what the H's are doing. So this would be our final answer for figuring out if it's endo or exo here. So in this problem, recognize that our diene is it has those symmetrical substituents at the end of the p orbital system. It just so happens though that they're symmetrical, but they are symmetrical in that they form a ring. So that's perfectly okay, but we know now we should expect either the endo or exo products here. We know endo will be more favored regularly. But in the last problem, we talked about doing that tool to figure out what the hydrogens are doing. And we said that when it's cyclic, it gets a little bit messier to do that. But luckily, um, when it is cyclic, you can predict very easily what it will look like without having to do too much thinking because it'll follow a general pattern. So in this case, we know that we're going to have a 6-carbon ring somewhere. So I'm going to kind of draw real quick. So there's your 6-carbon ring, right? And then we have to have this bridgehead. So if I color this bridgehead red, so we can show where it's going to go, that bridgehead would be right about here. And I'm trying to draw this on a wedge, or like it's coming out of the page. But it looks like it's kind of pointing up and out of this 6-member ring. And all 5-member rings are going to do the same characteristic type thing. So it's a nice pattern to follow. We know that double bond still needs to be there. Let's not forget that. And then the nitrile groups. So those will be pointing downwards. And so this will always be true for these types of problems when we're determining endo and exo. This would be the endo product. So the exo product, if you're curious, it'd be with these nitrile groups pointed upwards. So doing the same thing that this kind of bridgehead is. And I forgot to color it red, but there's that carbon. So another endo-exo problem, but let's go on to another regiochemistry type problem. Okay, so I kind of already said that we're going to have to worry about regiochemistry here, but let's try this problem first, and then we'll work through it together. So this is going to apply that first rule on that first slide of the video that I had up. So recognizing that the diene and the dienophile are both not symmetrical, we should expect that there will be 2 possible constitutional isomers. And obviously, there's going to be one that's going to be the major product. So determining which one's going to be the major product, we can kind of figure out by doing some resonance. So if we said that on the dienophile, the double bond moved up to kind of help stabilize this nitro group, which is a real thing, you'd see a partial positive down at this bottom carbon right here. And you could also say it goes to the other nitro group, that's just fine. But over on our diene, electrons that we should consider are the ones from our methoxy group. So if those came down, we'd have to push electrons to that carbon, and that would let us see a partial negative charge. And so we're not actually moving these electrons around. They're not actually our mechanism for this problem. It's just how we're going to think about what's going on. So for the most part, disregard these white arrows. They're not a mechanism. But we need to care about these partial positive and partial negatives. We know from general chemistry that opposites attract. So if we could match up our partial positive with a partial negative, that will give us the best interactions. So below, I'm going to draw the molecules the way that they're actually going to interact with each other. And I guess I could show the delta negative right there. I'm going to just flip upside down the dienophile like this. And I'll draw in the partial positive. And you can see that now when I start matching them together, they're going to come together such that the partial or the delta positive is going to interact with the delta negative, which is going to give us our best interaction. So our product, 6-member ring, double bond in the middle, methoxy group hanging out here, and then our 2 nitro groups are going to be opposite right here of that methoxy group. So on this problem, it looks kind of similar, but I promise it's a little bit different. But go ahead and give it a try, and then we'll work through the solution. So for this one, again, we should apply that first rule. Recognize that there's going to be a delta positive right here, because this is just the same exact dienophile that we had the last time. That's not going to change. You can have the same reasoning for it. But over here, Over here, our methoxy group's on a different carbon. So because it's on a different carbon, we have to consider the resonance doing different things here. So if we moved electrons down, we can either move electrons onto that carbon, or we can move electrons down into that kind of two sandwiched carbons. But if we did that, we'd have to finally move electrons to that carbon right there. And so that tells us we're going to have a delta negative right here and right here. So let me put it in red. This carbon and this carbon have our delta negatives. Now the first carbon doesn't really matter. The first red carbon doesn't really matter that it's delta negative because we know that the cycloaddition reaction doesn't actually interact with that carbon directly. So the second red carbon, the one that's at the end of the pi or the p orbital system, is actually the one that reacts in these Diels-Alder cycloaddition reactions. So that's the one that matters to match up with our delta positive. So it just so happens that the way that they're drawn right now are actually exactly how we want them to be matched up. So if we start to draw our product, again, a 6-member ring, double bond still in the middle. The methoxy group, we said kind of moved. And now these nitro groups are going to be right next to it on the neighboring carbon, just like this. And that's our product. All right, so this is going to be the last problem I have. Let's work through it real quick. So after working through it, we recognize that the diene is symmetrical. It's cyclic, and so we can predict what it'll look like with that bridgehead carbon, because we've done a problem like that before. And so now all we have to remember is that we have to push down our dienophile the opposite direction of that bridgehead carbon. And then it becomes a simple problem. So again, we are expecting the endo product over here. Endo product. And if we wanted to do or draw it real quick, what's going on. And then, and for the sake of the problem, I'll actually, again, label the bridgehead carbon red so we know what's going on. So you can see where that carbon's gone. And remember from the previous problem that we did that our dienophile has to be going down. It's a little bit weird because it's a cyclic dienophile, but it makes no difference. I'm going to draw it down like this. I know there's a carbonyl here, there's a carbonyl here, and then oxygens, or one oxygen, that connects them to. So it started out looking like it might have been an asked problem. This is actually the final answer, and it just followed that same pattern that we're used to from previous problems.